Hi, my name is Jingyi Xie. I'm the presenter for the paper Helping Helpers Supporting Volunteers in Remote Sighted Assistance with Augmented Reality Maps. This work was completed in collaboration with Shu Yu, Suyan Li, Yao Lu, Saeed Mansubila, and John Carroll. Remote Sighted Assistance, or RSA in short, is an assistive service for people with visual impairments. Aura and Be My Eyes are two prime examples of RSA services. Let's watch a short video from Be My Eyes to better understand the RSA system.
Establishing video connection. Through your smartphone, Be My Eyes connects the blind with sighted people through a live video connection. Simply choose if you need help or want to help by the click of a button.
That's a nice picture of you and your family, Caroline. Is it for a present? Yes, it's a photo from my parents.
One of the biggest hurdles for RSA services is the issue of scaling sighted volunteers. In this study, we assist untrained volunteers in indoor navigation, which is challenging and mentally demanding. We made 3 contributions in this work. First, we designed an interactive system to implement a high-fidelity, computer vision-mediated RSA prototype with augmented reality-based 3D maps. Second, to address the challenges of simulating the highly dynamic RSA paradigm, we evaluated the implemented system by conducting a controlled laboratory study based on confederate design and role-playing. Third, we find preliminary evidence that 3D maps and localization can benefit RSA agents, especially untrained sighted volunteers in indoor navigational assistance, by significantly reducing the task completion time and their mental demand, temporal demand, effort, and frustration. In our prior work, we identified several indoor navigation challenges during RSA and developed low-fidelity pictorial prototypes showcase potential applications for computer vision to support RSA interactions. We proposed several design ideas such as creating interactive 3D maps, localizing and orienting the visually impaired users in real time, and estimating the distance to objects. However, the implementation of computer vision-mediated RSA service requires specialized hardware such as lidar scanner, software technology such as AR apps for both users and agents, substantial bootstrapping efforts, which is creating and annotating 3D maps of user surroundings in advance, infrastructure support, such as low-latency wireless communication to transmit data between users and agents. And finally, access to visually impaired users who can perform a fixed set of deterministic and repetitive tasks. These requirements are major constraints for researchers to test new designs in RSA services. In this study, we made several design decisions to fulfill these requirements with manageable efforts. We developed a pair of iOS apps, namely RSA User App that only supports iOS devices with a lidar scanner, and RSA Agent app that can be installed on any iOS devices. We implemented these 2 apps with Apple's AR Kit, Reality Kit, and ThinkKit. Specifically, RSA User App can reconstruct 3D maps by scanning the environment, save the 3D map, and conduct real-time localization. An RSA Agent app can load and display the 3D map and receive real-time camera pose sent from the RSA User App. The implementation of the system consists of 2 phases, offline mapping and online RSA. In offline mapping, first, a sighted volunteer scans the indoor environments of interest using an iPad Pro with the RSA User App. Second, the sighted volunteer saves the scanned 3D maps and AR world map to cloud storage, such as Google Drive. AR world map is a file containing mapping states and anchors for relocalization. Third, the sighted volunteer downloads the 3D map files to a laptop, annotates the maps, and converts the format. This is one example of adding annotations of copier room. In the online RSA phase, the user downloads the AR world map file of the current surroundings to the RSA user app for relocalization. The RSA user app will continuously send the position and orientation of the camera to the RSA agent app. In addition to the real-time location and orientation on RSA agent app, the user's iPad screen will be mirrored to the agent's laptop as a live video feed, where agents can see the moving pedestrians or new obstacles that are not captured in pre-recorded 3D maps. The RSA agent interface supports standard touchscreen controls to browse the 3D map. Agents can translate the view with 2 fingerprints, from right to left and from top to bottom. They can zoom in or zoom out with 2 fingerprints, or rotate the view with 1 fingerprint. This is one example of how agents provide navigational assistance with 3D maps. As the user is walking, the pink solid shape on RSA agent app is moving simultaneously, which represents the user's position and orientation. In this work, we present a confederate-based study design to evaluate the system, which was informed by a blind advisor from a local NFB chapter. During an early evaluation, the advisor observed that blind participants could find new labels to perform the deterministic and repetitive tasks, and they could develop a mental map of the testing sites using their orientation and mobility skills, which could impact the study results. As such, we adopted a confederate-based design, where the confederate is the individual who participates in the experiment, but is not observed by the researchers. In this study, the confederate was a sighted participant who played the role of a user who had recently lost vision and had not gained sufficient orientation and mobility skills. We recruited 13 sighted participants to play the role of volunteers and conducted 13 on-site experiments. Each agent user peer performed 2 tasks per condition. In total, each peer completed 4 tasks. Condition 1 is using a 2D map, which is a baseline and agent's current practices in indoor navigation. Condition 2 is using a 3D map containing the user's position and orientation, distance band, and room annotations. Task 1 is to find a specific room with annotation on both 2D and 3D maps. Task 2 is to find a landmark that is not annotated on 2D or 3D maps, such as a trash can or water fountain. We find that 3D maps can significantly improve the agent's performance in task completion time, particularly in the task of finding unannotated objects. From agents' subjective assessment, we find that overall, 3D map is better in terms of reducing agents' mental demand, temporal demand, effort, and frustration, while not obviously increasing the physical demand. We also discovered 3 key issues describing how 3D maps affect agents' performance in indoor navigational systems. I cannot go into all of them in this presentation, but I will look more closely at navigational strategy. For the full themes and findings, please see the paper. Within the theme of navigational strategy, 10 agents believe that the detailed environmental information on 3D maps made the wayfinding easier, especially in the task of finding an unannotated object. It is shown in this quote. The water fountain is actually on the 3D map, so I just look around the map and then just choose the one I want the confederate to go to, and then just ask him to go there. Because you can scroll the 3D map, you can just see where the direction really is, and you can just move the 3D map to see the surrounding environment. So that may help me to make more accurate decisions. End quote. In this work, we designed an interactive system implementing a high-fidelity RIC prototype using AR maps and presented a confederate-based study design to simulate the highly dynamic RIC paradigm in control lab settings. And that's it. Thank you again to NIH, Dr. Zihan Zhou, Xinbing Zhang, Michelle McManus, and our reviewers. And thank you all so much for listening.